Good morning. Today we will study continuous functions. First of all, we define continuity in terms of pre-images. Suppose x and y are two topological spaces, then a function f from x to y is said to be continuous if for each open set V in y, the pre-image of V, which is a set of all the elements x of capital X such that fx belongs to V, is open in X. This definition can be compared with the epsilon delta definition for a function f from x to y, means from a metric space xt to another metric space yd to be continuous, where we define continuity like for each point x in X and each epsilon greater than 0, there exists a delta greater than 0 such that for each point y in X with distance between 2 points less than delta, we have distance between their images to be less than epsilon. So first of all, we will prove one lemma. Suppose x, y and z are three topological spaces. If f is a mapping from x to y, g is a mapping from y to z, and f and g are continuous functions, then the composite z of f, which is from x to z, is also continuous. To prove this, we consider any set W, which is a subset of Z, to be open. If W is open, W in Z is open, it means G inverse W, which is a subset of Y, is open because G is continuous and G is a mapping from Y to Z. And this, if G inverse W is open, it means F inverse of G inverse W, which is a subset of X, is open since F is continuous and F is a function from X to Y. And this implies G of F inverse W is open. And it means, by definition, G of F is continuous. We have one more lemma. Let x and y be two topological spaces and suppose that B is a basis for the topology on y. Then a function f from x to y is continuous if and only if for each basis element B belonging to B, the pre-image f inverse B is open in X. To prove this, first of all, suppose that each basis element B is open in Y. So if f is continuous, by definition of continuity, f inverse B is open in X. Now for the converse part, suppose each open subset V of Y is a union of basis element, and we can write V equal to union B alpha, where alpha belongs to J, and F inverse B is equal to union of F inverse B alpha, where alpha belongs to J. So if F inverse B alpha is open in X, it means F inverse B is open. Now we have one more lemma. Let x and y be two topological spaces and suppose that S is a subbasis for the topology on y. Then a function f from x to y is continuous if and only if for each basis element S belonging to S, the pre-image f inverse S is open in X. So to prove this lemma, first of all, we suppose that for each subbasis element S is a basis element in the associated basis B. So if f is continuous, then f inverse S is open in X. And for the converse part, each basis element B belonging to B is a finite intersection of subbasis element. It means B can be written as S1 intersection S2 intersection Sn. So if f inverse Si is open in X, then f inverse B is also open. We have some examples. If xd and yd dash are metric spaces, then the function f from x to y is continuous if and only if for each x belonging to x and epsilon greater than 0, there is a delta greater than 0 such that the open ball BD centered at x and radius delta is a subset of f inverse of ball BD dash centered at fx and radius epsilon. That is such that for all y belonging to x, dxy is less than delta, and we have d dash fx fy is less than epsilon. This is by the definition of ball. So if the distance between 2 points is less than delta, then we have distance between their images with respect to another metric d dash is less than epsilon. One more example, let Rd and Rd be the real number with the standard metric topology and Rc of f is the real number with the cofinite topology. Then the identity function identity function means Ix equal to x for all x. So if the identity function I from Rc of to Rd is not continuous, since open interval AB is not open in cofinite topology for A less than B. However, this identity function is continuous since R minus F is open in the standard topology because F is finite. For F finite. Here cofinite means or cofinite, the word cofinite refers to the fact that complements of finite sets are open. If f is a subset of x and f is finite, then u equal to x minus f has a complement x minus u, and x minus u means u is x minus f, so it is x minus f, which is f, and this f is finite. Also, the collection of TCOF is a topology on X. This may be proved by the definition of topology. One more example, each finite non-empty subset f of x is open in the discrete topology but not open in cofinite topology. To see this, note that f to be open, see TCOF. In TCOF, its complement x minus f would have to be finite. Then x is equal to f union x minus f would be the union of two finite sets and therefore would be finite. But this contradicts the assumption that x is infinite. We can say such finite non-empty subsets f of f exist. For example, each singleton set f equal to x for x belonging to x will prove the purpose. Now we define continuity at a point. We say that f is continuous at x if for each neighborhood v of fx there is a neighborhood u of x with fu subset of v. Hence, the function f from x to y is continuous if and only if it is continuous at each x belonging to x. We have one theorem. Suppose x and y are two topological spaces and f is a function from x to y. Then f is continuous if and only if for each x belonging to x and each neighborhood v of fx there is a neighborhood u of x such with fu subset of v. So to prove this theorem, first of all we suppose that if f is continuous, x belongs to x and v is the neighborhood of fx. It means u is equal to f inverse v is a neighborhood of x with fu subset of v. Hence the proof is complete. Now for the converse part, if v is open in y and x belongs to f inverse v, then v is a neighborhood of fx. So by hypothesis, there is a neighborhood ux of x with f ux subset of V. It means X belongs to Ux is a subset of F inverse V. Taking the union over all X belonging to F inverse V, we find that union of F inverse V where union of Ux where X belongs to F inverse V is equal to F inverse V. And this is a union of open set, hence it is open. Now continuity in terms of closed sets and closure. Suppose X and Y are topological spaces and F is a function from X to Y. Then all the three statements are equivalent. Number 1, F is continuous. Number 2, for every subset A of X, we have F A bar. A bar means closure of A. Subset of F A bar means closure of F A. For every closed L in Y, the pre-image F inverse L is closed. So to demonstrate that all these three statements are equal, we will show that first of all 1 implies 2, then we will show 2 implies 3, then we will show 3 implies 1. So first of all we show 1 implies 2. It means if F is continuous, then for every subset A of X, we have F A bar is a subset of F A bar. So to prove this, first of all we assume that F is continuous and A is a subset of X. Therefore each point in F A bar has the form Fx for some X belonging to A bar. So we must show that Fx belongs to Fa. Let V be a neighborhood of Fx. So by continuity, F inverse V is a neighborhood of X. Since X belongs to A bar, the intersection A intersection F inverse V is non-empty. If we choose Y belonging to A intersection F inverse V, then Fy belongs to Fa intersection V because Y belonging to A implies Fy belongs to Fa. And Y belongs to F inverse V implies Fy belongs to V. It means Fy belongs to Fa intersection V. In particular, Fa meets V. Since V was an arbitrary neighborhood of Fx, we can say Fx belongs to Fa bar. Now we will show 2 implies 3. 2 implies 3 means for every subset A of X, we have Fa bar, subset of Fa bar. Then we will show that for every closed L in Y, the pre-image F inverse L is closed. Let L is a subset of Y which is closed. Let A is equal to F inverse L. Now we will show that A is equal to A bar so that A is closed. Now Fa is a subset of L. So Fa is a subset of L since L is closed. By hypothesis, Fa bar is a subset of Fa. So Fa bar is a subset of L. Hence A bar is a subset of F inverse L is equal to A. And this implies A is equal to A bar because we know that A is always subset of A bar. Now we will show 3 implies 1. Means for every closed L in Y, the pre-image F inverse L is closed, then F is continuous. Let V is a subset of Y be open. Then L is equal to Y minus V is closed. By hypothesis, F inverse L is equal to F inverse Y minus V. F inverse Y is X or minus F inverse V is closed. So F inverse V is open because if it is closed then its complement is open, hence F is continuous. Thank you.